Okay, let me try to get serious here. I have been talking about the Bohr model being wrong since I was in the Army in 1968. It was just impossible. And I said everything has to be a dipole. You can't have just one gigantic positive in the center, little tiny negatives. It doesn't work. And with the same charge even. They're just not correct. So I have always said they have to be dipoles. I could never figure it out. Trust me, I was no genius at that. I did the best I could. I couldn't figure it out either. But I did know that it was not a gigantic positive core and some neutrons in there, but it's basically a positive nucleus, which is the center, and then a bunch of little tiny, tiny, tiny electrons. They think they're so tiny they don't even consider them like they're nothing. Well, they're basically the same particle, which is electrons and protons, you would think, but they're really muons and electron neutrinos, they call them. And they see these. They know they're there. And they'll be talking about them. They've seen 1,000,000 collisions. They took 10 years looking through it. Wait till I read you the article. This is just stunning. And they did find these particles, and they said, ooh, they're really, really heavy. We had no idea how heavy they were. Well, I've been showing how heavy they are, and they're really like almost the entire mass of this particle. And this is what we would always consider an electron to us. And what is an electron? Well, it makes electricity. It's a spark. You get static on you and you touch a water pipe and you see the little spark. That's electrons jumping across, heading to what they call ground. And that's exactly what it is, because the ground consists primarily of these black balls. They are gravity. Muons are gravity. They are ground. They are the attractor of the electrons, which you build up on you in a dry environment, because they normally would be attached to water molecules floating around, and they'd be sort of not worrying about you. But you're more attractive to them when there's less humidity in the air, because they want to be attached to something moist, and you're kind of moist and tasty, and pip, they jump onto you. However, if they can get to ground, that's where they prefer. You touch a water pipe, and then you go, ah! You know, if you're a baby. You know, you really go, ooh, ah, ooh, if you're big and strong. Now, one of those is an electron. Also, it goes through wires. And what kind of wires does it go through? Copper wires, primarily. Other metals, yes. Copper is the best. Copper is just absolutely saturated. Saturated with extra electrons. Not just what forms the copper itself. There's just a ton, like a river of electrons in copper. That's why they use it to conduct electricity. It just goes right through there. And what's moving is these particles. And what has to happen? One of them is either sucking or pushing. Now, this electron here will push, and it's push to shove. If I'm up against another one of these white particles, we're going to fight each other. I'm going to push you, you're going to push me. This one here attracts everybody. They love everybody. The black particle says, come on, come to me, white particle. And it says, the other black particles, come on, no problem, everybody get together. This is what they like to be, is in a mass. Well, photons are the smallest, basically stable mass of particles, which are 2 electrons. So one of these electrons is here, and the other one upside down is here. 2 little bar magnets. All right, so you're with me so far. And that is light. And that light comes through the air, and you can't see it normally, but we found a way to see it, and I will show you that. It has a field of magnetism surrounding it, just like a rubber ball. And when it hits something, it bounces. And it depends on what it hits, how hard it bounces back. And how hard it bounces back depends on what color you see. If it comes back really hard, you're seeing white. If it comes back really soft, you're seeing red. If it comes back in the middle, it's yellow or green or blue or whatever. But it depends on this bumper pad bumping and whatever it hits. That's why the same light coming in here hits all these different things, gives different colors, because all of these different things are made of different mushy materials. One of them's mushier than the other. Black absorbs everything that hits it. White tries to bounce almost everything back. Anyway, there's a lot to know about this, but it's simple. This bounces. This pretty much won't kill you. This will kill you if there's enough of them. If you just get enough static on you and you zap something, well, you know, you're not going to die from that. If you get by lightning, well, that's a different story, you know, and that's just nothing more than a ton of these at one time. Same thing with electricity. Well, depending upon your resistance to the electricity and how strong the electricity is, that depends on how explosive it is in your body. Because you cannot absorb so many extra electrons. You can't absorb them fast enough. If they're being pumped into you like an electric chair or lightning, you're just not going to be able to take it. And then your molecules explode because they have no way to deal with so much extra energy coming into them. And that's how you get literal explosions. So this is my model. Now, guess what? At this point, I believe they agree precisely with what I am saying. Fermilab specifically, and I will do this because Fermilab agrees, this is a fixed particle. Fixed means that it's just the same size. I agree 100%, that's correct. And this is a point particle, which can change its size and glow and give energy, you know, all kinds of burn power. This one's a bowling ball. That one's a nothing. It has no mass to it that I can determine. And here's what I've come up with. And this is what they do say. 99.5% of all mass there is, all mass that exists, is these black particles. And they are gravity, they are dark matter, they are an attractive thing, they are heavy, they never change. We were able to separate them from the electron neutrino, the white ball, and see that we can make these can change. We can see that, right? Absolutely no question whatsoever, and these don't change. That also, I believe, there is no question about that. And we have shown that. And we have shown them together as an electron, and we have shown them together upside down, back to back as a photon. So we have really demonstrated everything they're talking about right here. And it says that tiny particle may upend physics and our own understanding of the universe, and it absolutely has. And it is electron flood theory. Dipoles are electrons. Not the electron just being a negative little glowy, sparky little bugger. It's got a dark side, as we all do. Okay, my friends, this is really going to be fun. And this just came out April 7th, 2022. Tiny particle may upend physics and our own understanding of the universe. And it does, 100%, because they have discounted these particles, and I've shown them. It says new research shows that W boson, a tiny particle fundamental to the formation of our universe, is heavier than scientists expected. Well, what is a W boson? Well, that is what it is right there, really. It's a muon. They call it a W boson, but it's really the black particle. I'm going to call it the black particle. So the W boson is heavier than expected. It's just a bowling ball. This discovery goes against the scientific model of particle physics. Absolutely, because it's been wrong since Bohr introduced it. That is the framework scientists use to make sense of all observable matters. Now, I've been going after Fermilab for several years now, a number of years, about my particle discovery since 2015, for sure. Now, they just assigned 400-person team, carefully sifted through 10 years' worth of data from more than 4 million collisions in a Fermilab particle accelerator. And what did they find? They found that these particles are just big, solid, heavy-duty black particles, which I have been showing. All right, so you know that I have been against the standard model since I was in the Army in 1968. It just wasn't right. It still isn't right now, and they know it isn't right. Now, it says, according to the standard model, this W boson, together with another particle, which is these two particles together, called the Z boson, they keep making up these names, are responsible for the weak nuclear force. Well, they are in the nucleus, yes. One of the four forces that hold together all observable matter in the universe. Well, I don't know about that. Let's talk about it. The other forces include gravitational force, which is the black ball. That's the one that holds the gravitational force. How it does it, I don't know. It's exactly opposite of this one. So it says the other force includes the gravitational force, which nobody knows about because it says which there is currently no explanation for in the standard model. You drop something and they don't know why it hits the ground. Well, it hits the ground because most mass is made up of these, and these are extremely attractive to the white particles, and I've shown that. And I think now I have a little more different interpretation of how these interact. I always thought that the white was the one we wanted to collect for the energy, and I think we still do, but it's really the black that sucks the white one to it. Or I believe it's that way. It's not that the white is doing any attracting of the black. I think the black is attracting the white, and that's where the energy is. So we have to collect the white somewhere, feed it back into the black. Anyway, that's a whole other issue about getting free energy. Because now that we understand what these particles are, we should be able to use this. Because I've been able to separate these particles, the black and the white, from each other. That is fission. If you could separate them, that's fission. And this is subatomic nuclear fission. And then they come right back together instantaneously. And they say they know that. It's right in this whole article. It says exactly what I'm telling you right now. So it says there's one of the four forces that hold together all observable matter in the universe. The other forces include the gravitational force, no explanation for that whatsoever. Electromagnetic force, which is the attraction of those two, that's what the electromagnetic force is, and the strong nuclear force. The strong nuclear force just means at a certain resonance value, boom, they lock in, and then they are strong. So I agree with everything they say here, only I don't think they understand what they're saying. All right, they say it right here. The W boson, one of the tiniest, there's only two tiniest. One's the W and the Z boson, if you want to call them that. I thought they were calling them a muon and an electron neutrino, but whatever you want to call them, it's that little black and white ball. Now, they're the most elementary particles in the known universe. 100% agree with that. Causing a big ruckus. Yes, I have caused that big ruckus. I've been showing these since 2015. And I claimed that these particles are dark matter as they approach Earth, coming from the sun and every other luminous body in space, and they are atomic vapor. I've made the statements forever. So now they finally decided, because I've been really stamping my foot down. That's what's going on. I've been screaming. I'm the only one screaming about this. So they said new findings about the particle fundamental to the formation of the universe suggest its mass may be far heavier than predicted by the standard model. This is the theoretical rule book that helps us make sense of the building blocks of nature, of matter. If true, it could signal a monumental shift in our understanding of the universe. Exactly. You can't understand something if you don't understand what it's made of, and they don't. They've been smashing particles together, huge protons and billions of particles at the same time, and now they have 400 guys sifting through these particles, these pictures. Well, here's what it says. They have 400 guys looking for particles in there, and they did. But 400-person team. They went back and looked at 10 years worth of data from more than 4 million collisions in the Fermilab particle accelerator. Okay, my friends, it just doesn't get any better than this. I've been saying these are fixed particles. They are just like bowling balls. They do not change, and they are heavy as hell. These are just burners, and this is a photon of light. We did some experiments with a Venturi, and we were able to actually use photons of light and see them. Not only can we see the red, we could see the green, and it is identical but extremely powerful. All right, there's the green as well. You can see, and it is very powerful compared to the red, because we put them through the same slit at the same time. I'll show you. Okay, as I showed you, they're the exact same particles, but this one is hot. That's coming in really hot. This one's coming in just kind of mild. Then the green just pushes the red away. And then the green reconcusses way out there. So you can see its extreme intensity compared to the red, much more powerful. Okay, so what have I shown you? We took red pulse laser, green, blue, all of them, and accelerated them through a venturi. It looks acceleration to me, but at any rate, right here they divided the black and the white particles. I showed you the black and the white attached, and right here they're in that little box formation attached. And this is what they look like as they approach that venturi, and then the black and white separate, as I show right here. And you know, that's exactly what CERN and Fermilab are looking for, is that separation to move the black ball, which is the heavy, dense, extremely heavy particle. I mean heavy. I'm going to show you. You won't believe how heavy that thing is. And I can prove how heavy it is by an atomic bomb blast, and I'm going to show you right now. So this is fission. They broke apart, and this is fusion. Can we use this to generate energy? I think maybe. And this is cold, because we didn't use any extra energy whatsoever. All we used was a Venturi device to force the fields to crush into their own selves instead of hitting them head on. They had them one come this way, one come that way, and they smash these huge protons. And then they dig through all the debris. What do you see? They did have 400 guys digging through all this debris to find the particles that I've been showing them, and they found them. Alright, I told you there's a big heavy-duty black particle, and then there's a really fluffy, almost nothing particle. This is the big black one. I show you attaches to a little white one. Or, you know, it's normally white. We're seeing them as red and green as their energy levels. However, the white one can get big and little and just glow and shower and all that stuff. The black one absolutely never changes. It's heavy. It never ever changes. It's like a bowling ball. It's attractive as hell though. It wants the white ones to come right back to it. And I believe it's dark matter. And the reason I say that is because it does not emit light. It does not absorb light. It does not reflect light. It's just a black particle. It doesn't do any of those things. It attracts everything extremely gravitational. It doesn't mind being right on top of another one of these black particles at all. The white ones are completely the opposite. They are light, almost no mass whatsoever that I can determine. They are burny as can be. These are cold. Those are cold. These are hot. They reflect, they absorb, they emit, and they are not dark. That's for damn sure. Now watch this. This is an atomic bomb blast. Now my interpretation of the atomic bomb is the first thing that comes out is the white particles, and then following that is those heavy bombarders. You're going to see nothing but burn, and then you're going to see explosion. The burn is the white, the explosion is the heavy-duty 99.5% particles. So the first ones that are going to hit are which surround everything is the electrons. So those are going to go first. And these are, electron neutrinos. I call them, the two of them together, I've always considered to be an electron because that's what moves through wires and so forth, and it's electricity and lightning and all that static electricity. That is because the black particle is always attached to the white, always, always, always. The only time it comes apart is during these really, really intense events where fields crush other fields, such as an atomic bomb, or exactly what we did by forcing them to concuss through that venturi. We created an atomic event on the desktop for free. Now this is an atomic event that was not a real pleasant one. Now this is the Atom Central channel, and this is the Teapot Dome, Teapot Apple experiment where they're blowing up houses to see what the atomic bomb would do to them. So I have it running extremely slow. So what we're going to watch is the first thing you're going to see is just 100% radiant energy, total whiteness. And then you're just going to see this thing start to burn. Nobody goes anywhere. It just burns. It just burns. That tells me there's no impact value. There's nothing more than energy. Energy appears not to have any mass to it. This is very new stuff. All right, watch. Here it goes. Now, you're going to all of a sudden see a flash. Boom, there it is. Now it's just burning. That's all it's doing is burning. Nobody's going anywhere. Now watch what happens when the black guys come, the black balls. Boom! It's going to just go flying. There it goes. Now, I just stopped it for a second because I want you to take very, very careful notice of this. Nothing here is burning anymore. The white ones have done their job and burnt everything on the surface. Now, that just comes and forcing it. However, it'll turn around and come back. That is not what you expect from a bomb. You expect it to blow out and just keep going. Well, this stuff is going to turn back and come back. And why would it do that, Roger? Well, the reason is because the black particles back there are gravity. And they've lost all their white particles. They say, come back. And they do. And watch carefully. Watch what happens. It's all going that way now. You see it's sort of stopping. And it's saying, whoa, 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 let's go back to see that guy. And here it comes. All right, that's what nuclear power is all about. It's once you lose all that white matter, it wants to come back. That's the gravity. All right, we found that tiny little particle, and it does upend physics 100% because it proves my electron flood theory, to be honest with you. Everything is a dipole. Now here's what they say right here. New research shows the W boson, a tiny particle fundamental to the formation of our universe, is heavier than scientists expected. It is, now they say it's 99.5%. Now, this discovery goes against the standard model of particle physics, which has been wrong forever. The framework scientists use to make sense of all observable matter. That's why nothing makes sense. 400 people they had working on this team carefully sifted through 10 years worth of data from more than 4 million collisions in the Fermilab particle accelerator. That's who I've been sort of needling as Fermilab because they wouldn't listen to me, and we went back and forth. You know, I had just certain contact there that we went back and forth, and I see they finally went back and looked at it. I applaud that. The W boson is one of the tiniest, most elementary particles in the known universe, is causing a big ruckus in the field of particle physics. Thank you, Fermilab, for finally looking into this. New findings about the particle, which is fundamental to the formation of the universe, suggest its mass may be far heavier than predicted by the standard model of particle physics. The theoretical rule book, which is wrong, that helps us make sense of the building blocks of matter. No, it makes no sense. If true, it could signal a monumental shift in our understanding of the universe, and it does, because it is true. All right? According to the standard model, the W boson, which is the big black heavy-duty jobber, together with another particle called the Z boson, which is the little weak, well, not weak, it's just a Bernie particle. It doesn't have the impact as the W. You saw how the W boson just pushed the house away. The Z boson just made it burn. So they're responsible for the weak nuclear force, one of the 4 forces that hold together all observable matter in the universe. The only force that holds anything together is that black ball, because they still are totally lost. They're still trying to stay with the Bohr model. Doesn't work. All right. So they hold together all observable matter in the universe is what they're thinking is. The other forces include gravitational force, for which there is currently no explanation in the standard model. It's the black ball. Electromagnetic force, we just saw that, and the strong nuclear force. They've making all these different determinations based on the wrong starting place. You know, gravitational electromagnetic forces work across large scales. Yes, it's nothing but dipoles. Okay, so I think I showed you already that Fermilab has had 400 guys looking over all their past tests that they did for the last 10 years, and they found millions of these interactions. Well, I'm going to show you right now, from an atomic bomb blast, the first thing that goes out is the white particles, all right? And the white particles only burn. They have no impact value. The black particles, exactly what Fermilab says, are much heavier than they had expected. And these are the ones that explode the house. Now, I have this on very slow playback, and this is already in slow motion. But we're going to see how this progresses the nuclear explosion. Now, this is called the atom central channel, and this is going to be how they test the nuclear bombs against building materials. Okay, so here goes. Alright, now I'm going to stop it as it hits. Alright, the first thing we're going to see is a real splash of just, see the whiteness? I stopped it. Whew, everything just glowing white. Well, what is it doing now? It's absorbing all those white particles, and it's going to get to a point where it can't absorb it anymore, and then everything's just going to flame up like this. But no, there's no impact. Nothing moving yet. Watch. Nothing moving. Not a thing is moving. Now it's absorbed, and it can't accept any more electrons, and everything just goes into flames. It's all the combustibles are just gone. But the house never moved. Now it's moving. Now the black balls have come. They don't burn. They push. Just like Fermilab says, they're much heavier than they thought. And boom, there it goes. Now, what else do? They are gravity. So, what would happen? On the place where the bomb went off, the black matter would have gone to the center primarily. The white stuff will never stay close to each other. That went first. That all goes. So the black stuff comes after, but not all of it. So what does that mean? That means we've got literally a ball of gravity sitting on the tarmac where the bomb went off. Instead of having that coated with all of these, normally it was sitting like this. It explodes. All the little white glowy particles are gone instantly because they surround the core. So the core follows it with a bunch of its particles, but a lot of the core stays. So what happens is the little glowy ones are out there, and the core says, hey, I can't live without you guys, come on back. And they do. They turn around and come back. You watch. It was going this way. You'd expect it to just continue. Watch what happens. It turns around and comes back. It's stopping now. Watch it come back. You see that stuff coming back this way? Look. Swoosh. Right back at us. That's because the black says, come on back. All right, so what have I shown with this test house? I say the nuclear package sits somewhere when it explodes. It's the primary thing that happens is they force all the electrons in against themselves, and then they all bounce back out. So the white stuff goes out first. Then the black stuff comes after. The white stuff has no impact value, none whatsoever that I can tell. I mean, you could see just barely rolling over the line, just barely moving. Nothing broke. No, not even any windows that I can tell. It just burned. Let's go with it a little more. You can see it's just fuming. There's not one single stick has broken yet. And all of a sudden, you see it? It's just nothing but vapor coming off. So my estimation here is it has absorbed so many electrons so quickly that everything has just vaporized, but nothing's moved. Now comes the bowling ball blasters. There they are right there. Look at that. Now they don't burn anything. You're not seeing any more burning. And all of a sudden they turn around and come back. Swish. And they come back because what was left there after those white ones left was almost nothing but this. And it cannot exist without those white ones to come back to coat this. That is the way black particles are. They desperately want to attract back these white particles. So I sort of used to think it was the white that was desperately seeking the black. But I think it's the black desperately attracting the white. I guess it's the same thing. I mean, what's the difference? But there's going to be some kind of a difference when we try to figure out how to store this. So there's a little complexities here as to what pushes what and what shows what and what sucks what and what, but it's, you can see there's two obviously different interactions. No question whatsoever. One's a burny blast, smoky burner with no impact, and one of them is an impactor with no burning stuff going on. Best I can tell you.